All right, let's get started. Welcome, everybody. I hope you enjoyed the keynote. This is the WebGL Techniques and Performance talk. My name is Gregg Tavares. I'm a member of the Chrome team on the GPU part of that team. If you're going to tweet about this, we ask that you add the Chrome hashtag. And also, there's a link up there that is a Google Moderator link where you can, if you think of questions during the talk, you can put them on there. And at the end of the talk, we'll take the top questions. You can also vote on questions. And there's also 2 mics if you don't feel like putting them there. But it might help you remember your questions. So how many of you have used WebGL? Raise of hands. All right, good. How many of you who haven't used WebGL have used OpenGL with shaders? All right, quite a few of you. OK, that's good, because this is a 201 talk. So it's kind of assuming that you've used WebGL. I'm not going to go into like tiny little details that you might need to know if you haven't. I will give you a short overview of WebGL, so hopefully you'll be able to follow along even if you've never used WebGL before. I'm going to go over drawing a lot of objects and different techniques to optimize that. I'm also going to go over a few post-processing techniques, a few general do's and don'ts, and some tips. So WebGL, if there's anybody out there who hasn't used it, it's standard. It's built into most modern web browsers. It's not a plugin, and it provides access to the system's GPU. And so it's actually really simple. At a conceptual level, you have 2 functions that run on the GPU. And so the whole API, the WebGL API, is there to help you get all your data and these 2 functions set up on the GPU so you can tell it to run these 2 functions for you. And so those 2 functions are represented in green in this diagram. One is called the vertex shader, and the other is the fragment shader. The vertex shader is responsible for processing your mesh. So if you've ever seen any 3D, worked in any 3D, you see that, like if you watched a Pixar making of or something like that, you see that 3D models are made out of vertices and polygons. All that data goes in this blue box on the screen, your buffers. And then you, through something called attributes, you describe how that data is delivered to your vertex shader. Your vertex shader, as far as WebGL is concerned, only has one responsibility, and that is to fill in this global variable called GL position. And it fills that in clip space coordinates, and I'll explain that in a moment. You also have something called a fragment shader, and when the GPU renders your triangles or your graphics, it calls your fragment shader and says, what color do you want this pixel? And so the fragment shader's only responsibility is to set this global variable, GL frag color, with the color you want the next pixel to be. Both of those shaders can take some inputs or parameters, and they're called uniforms in WebGL. And a vertex shader can pass data to the fragment shader through something called varyings. And so you can see that it's fairly simple. Another thing that I like to point out is that WebGL is actually a 2D API. Of course, everybody's doing 3D with it, but at a base level, it's a 2D API. And I'll show you what I mean. So the first thing is, this is the simplest vertex shader you could write. We're just going to take a position from our buffers, and we're just going to store it in that global variable I mentioned a moment. No math, nothing special, straight into that variable. This is about the simplest fragment shader you can write. We're just going to say every pixel is red. If we give it some data that's already in clip space coordinates, so clip space coordinates are basically, no matter what size you're rendering, no matter how large your canvas is, they always go from -1 on the left to +1 on the right. They go from +1 on the top to -1 on the bottom. And so if you give it clip space data and say, draw that, you'll get that result. There's this data for a square. Here's a square on the screen. You're the one who adds the 3D. You do that by modifying your vertex shader. So here's our original shader on the left. On the right, we've just added 2 lines. We've added the ability to pass in a matrix, and we're multiplying that matrix, multiplying the position we're passing in by that matrix before storing it in that global variable we mentioned before. We can compute that matrix in JavaScript. So here is some kind of pseudocode. The first part is computing a perspective matrix. The perspective matrix is what actually takes your 3D data and converts it to 2D. A look-at matrix is what's considered the camera or the view. It says where the camera is in the scene. A world matrix is usually the matrix you use to orient something in the world and rotate it and position it. You multiply all those together and set them into that matrix uniform. And then if you call it, you'll get that same data looking like it's perspected in 3D, when in actuality you took that 3D data and converted it to 2D by adding your own math. And so that's the unique thing about WebGL. It's really 2D, you add the 3D, and all of WebGL is really about how creatively you use those two functions, the vertex shader and the fragment shader. So I'm going to go over drawing lots of objects. So let's say we want to draw 100 objects. If you want to draw 100 objects, you can pretty much do anything. WebGL is pretty fast, and 100 objects is not going to tax it. You can use any library that's out there. You have a typical model-based library. I have some pseudocode here, so assume that I have an array of models, and this code is for each model. It's going to pull out that model. It's going to call this function useProgram. That's the function that uploads your two functions, your vertex shader and your fragment shader. Together, they're called a program, and uploads those to the GPU. I have a function here called setUpAttributes that would tell it how to use our mesh data, and that's representing a bunch of calls into WebGL. SetUpUniforms would set up our parameters. And then finally, GLDrawElements is what draws that object on the screen. And so if I show you a sample of that, here are 100 objects. And you can see that, I don't know if you can see that from a distance, but it's running at about 60 frames a second, which is about as fast as you're going to get. The monitors usually refresh at 60 frames a second, so you're not going to go faster than that. But let's say we want to draw 1,000 objects. So we can use that same technique and try drawing 1,000 objects. And you can see that we're now down to about 30 frames a second. It's running slower. So we need to do something about that. So what can we do? So one thing to notice is that most apps draw many instances of a few objects. In this particular application, there are only 3 objects. There's a square, a cube, a sphere, and a cone. And so why am I executing these heavy steps in my inner loop? And those heavy steps are these 3 red steps. UseGLProgram is a very heavy step. It has to upload your program to the GPU. SetUpAttributes may have to call from 15 to 30 GL functions to set up all your attributes and tell the GPU how to use your data. SetUpUniforms as well could be 5 to 20 calls. And we're doing that 1,000 times every frame. And that's going to add up to a lot of time. So what if instead, for each type of object, like for each type of object, in this case we have sphere, cube, and cone, set up what's common to that, and then for each instance of that type of object, set up what's ever unique, and draw that instance. And so here's the code changed a little bit. I sorted my array of models by the model type, and then I have a variable last model that I can remember which model did I just draw. And inside my inner loop, I'm checking, is the model I'm about to draw different than the model I just drew? If so, then I'm going to set up this program for this new model and set up the attributes, and again, set up the uniforms, but this time I'm only setting up shared uniforms. So for example, shared uniforms in this case are like the lighting. The lighting is the same for all 1,000 of those objects, so I only need to set it up once. At the bottom, I'm still calling setUniforms again, but this time I'm passing in unique uniforms. And in this case, unique uniforms are like its position in the world and the color of each object. And so in that particular case, we went from 1,000 times setting up these things to 3. Because we only have 3 types of objects. And so if I go back and I run this optimized version, you can see we're up to 45, 50, it depends. But definitely better than we were doing at 30. So that's the first thing you can do when you optimize. And that's a pretty generic technique. You can use it almost anywhere. One thing to notice, though, is that I was sorting that model, sorting those 1,000 objects every frame. And of course, that's just an obvious suggestion, is that if you can move that sorting outside of your rendering, maybe do it at setup time or organize your code so that all your models are in separate arrays. Whatever you can do, use some kind of insertion sort as you add and remove objects. Whatever you can do to keep that sorted, you could save yourself from sorting it at the last moment and keep your speed up. But let's say I want to draw 10,000 objects. So let's use that same technique with 10,000 objects. So now we're running at 5 frames a second. And 5 frames a second, yeah, that's pretty bad, but it depends on your application. Maybe you're going to do something static or that doesn't animate that often, and that's OK. But let's try optimizing it. So the first thing to notice is how much work is JavaScript doing. So in our current code, we have a loop. It's going over 10,000 models. And for every model, it is computing a world matrix. That's the first line here where it says M4 translation. And M4 is a reference to a JavaScript math library that I'm using. And then it's multiplying the world matrix by the view projection to get a world view projection. And that was the example we showed at the very beginning when I showed the simple 3D shader. if you want the minimal math in your shader, this is what you'd end up doing in JavaScript. But those two things represent a lot of work. So making a translation matrix is filling out a 16-element matrix. Multiplying two matrices is 64 multiplies and 16 adds or something like that. It's a lot of work. And we're doing that 10,000 times per frame. Great. Thank you, Microsoft. I think they did that intentionally. So WebGL support in IE. Well, we will hammer our best on Microsoft and convince them to add it. Until that time, you have Chrome Frame if you're running IE. And it runs great, and WebGL performs excellent there.
Does this demo work in Linux?
This demo does work in Linux.
Have you considered using Linux for this demo?
If I had a Linux machine set up, I would have considered that. Sorry about this. What other questions can you come up with where we're wasting time? The math library I'm using is called TDL, or 3D library. You can find it at 3dlibrary.googlecode.com. There's also a benchmark. If you search for WebGL math benchmarks, I'm sure you'll find one that's kind of comparing these. And it's getting the different library makers to make their libraries as fast as possible. And it's also getting the browser developers to look at those benchmarks and speed them up. So obviously, all of the browser developers are trying to be the fastest browser out there. And we take those very seriously, and we definitely are speeding it up all the time. In fact, I actually had to change my talk in the last week because one of my optimizations was based on JavaScript being slow, and V8 got faster, and it no longer made sense. WebGL is based on OpenGL ES 2.0 with 0 extensions. So that's pretty much like the same. Well, iPhone and Android both use OpenGL ES 2.0. What else uses it? Chrome OS uses it. WebGL uses it. It's similar to OpenGL, but OpenGL's had a lot of things have been removed in OpenGL ES, which makes it more streamlined. Okay, where were we? So we went through this optimization, and I was just about to show you. Right. So before we were doing all this work, we're doing this, creating this translation matrix and doing this multiply. That's very expensive work for JavaScript. So what if we move that work to the GPU? So instead of actually generating those matrices in JavaScript, let's just pass the position up to the GPU and let the GPU create those matrices. So we're changing the JavaScript, so we just give it the position. Here we're taking the position of one instance and setting it into a uniform and then calling set up the uniforms. And this is how we change the GPU or the vertex shader. So the old vertex shader was multiplying by the world view projection that we're passing in. The new vertex shader, well, we're only passing in world position. This is the code that will build a world matrix. This is the code, and instead we're going to pass in view projection. And this is another advantage. Not only are we not computing a world view projection in JavaScript for every one of those 10,000 objects, but the view projection is global. We only have to pass it in once. It's the same for all objects. So we're saving the time of even passing it in on top of computing it. And then you can see at the end where we actually use it, those lines haven't changed. The only thing that's changed is whether we passed in the world view projection computed from JavaScript, or that we only passed in a world position and computed it inline. And so if I show you that example, we were running at 5 frames a second before. Now we're running at about 7, 8. So it's running a little bit faster. But that's really not good enough, right? We want to do better. So what are we really doing? Right now, we're drawing 10,000 objects, and for every one of those objects, we are and currently we're setting up a world position, but before we were setting up a world matrix, we're setting up a color, and then we're calling draw, and we'll get it, say, one of these cubes. And we set up a new world matrix and a new color, and we call draw again, and we get another one of these cubes. And on the left, that represents the cube data, right? There's only one cube in memory, a mesh for one cube, and we're using it to draw multiple cubes. But what if instead we put all the cubes in one mesh? And we'll add some extra data so we can actually treat them as though they were separate meshes. And so what do I mean by that? Well, I'm going to take the data for one cube, and instead of just having that one cube, I'm going to repeat it inside our buffers, basically 10,000 times. And I'm going to add 2 more columns of data. I'm going to add a world position column. That world position is the same for every vertex of cube 0, and then switches to whatever the position needs for cube 1, but it's the same for every vertex of cube 1. And the same with color. The color is repeated for every vertex of cube 0, and then it's repeated again for whatever color cube 1 is for every vertex of cube 1. And in this example, we were going to draw 4 cubes. Well, we ended up being able to draw them with one draw call. And so instead of JavaScript making 4 draw calls for 4 cubes, we'd make one draw call for 4 cubes. And that should save us some time. Again, we have to change our shader. So we had our old shader. Our new shader, we're passing in we're getting our world position from these buffers. And we're going to compute the world position by just adding it to the position of the individual vertices of our cube at the origin. And again, we're only passing in view projection, so we save that time because it's global. We also have to pass in our color. We're getting our color out of our buffer, and we're going to pass it through a varying over to the fragment shader. The fragment shader used to have a color that we passed in where we changed it before each draw call and passed that in as a uniform, but now we're getting that from the vertex shader. So what this means is there's very little work going on. Well, I shouldn't say there's no work going on, but there's only a couple draw calls. And actually, it's one of the things you need to pay attention to when you're trying to optimize for WebGL. The fewer draw calls you can make, usually the faster it's going to run. There's one thing. We're still updating a lot of vertices. We have to update the world position for every vertice of all 10,000 of those objects in JavaScript. But let's see how it does. So now we're running at 24 frames a second. That's a lot better than 5 or 8. That might be good enough. Let's take it to the next level. Let's say we want to draw 40,000 objects. So we'll use that same technique, and we'll draw 40,000 objects. And we're running at about 13 frames a second. That's actually pretty impressive when you think of what's going on. I'll tell you what I mean. What is JavaScript actually doing? Well, JavaScript is actually computing 40,000 positions every frame. It's updating the world position of all the vertices, and those objects, they're an average of 21 vertices each, so that's 852,000 vertices every frame. That's 2.5 million values, because every vertex is an X, Y, and a Z. It's got to update all 3. And it's doing it, what was it, at 15 frames a second? That's like 37 million operations a second that JavaScript is doing. I mean, some of those JavaScript engines are doing pretty amazing. But let's see if we can make it go even faster. So one of the things we're doing is that we're computing for those 40,000 objects. Each instance of those objects has a clock in the current implementation. So you can see here, we're updating the clock in each axis of a particular instance. Each axis has a speed, each axis has a clock. We're taking the elapsed time and advancing those 3 clocks. And then the way these objects move is they kind of move in a kind of a spherical spirograph function, which is what this math is doing. So each axis has a radius, we multiply it by the clock, and we get this spinning motion that you saw. The problem with that is that their state, going back here, every instance has 3 clocks. So there's 120,000 clocks that we're updating, and they stay persistent from frame to frame. What if instead we just have 1 clock, and we compute where those clocks would be every time we need them? So we just have 1 clock, and instead we have an offset for each of the individual clocks for all 120,000 clocks. We can take our global clock, we can multiply it by the speed, we can add where the clock started, and that will give us the same answer. But we're not actually storing any result. We only need it temporarily, just long enough to draw. This math stays exactly the same. But what does that do for us? Well, if there's no state in your computation, then you can move that math to the GPU. So what do we have to do that? Well, we have to add the data we needed. So we're going to get rid of the world position from our data because we're going to compute it now. And we're going to add our clock offset, clock speed, and clock radius to our buffers. And again, they're repeated. So those values will be repeated for each vertex for a single cube, and then for the next cube, there'll be unique values for each vertex of that cube. So here's our shader again. We're back to our old shader at the top. The new shader, we're going to pass in our clock. We're going to get our clock offset, speed, and radius from our buffers. And before, like in JavaScript, we did this in 3 lines, but in the shader, we can do it in 1 line because that clocks is a vec3. Vec3 has an x, y, and a z. Clock offset has an x, y, and a z. Clock speed has an x, y, and a z. So that's actually doing all 3 clocks at once. This line, we're pulling out our spherical coordinates and putting them in a temporary. And then we're computing world position. And again, t has an x, y, and a z. Radius has an x, y, and a z. So a lot more is happening there than was in JavaScript in a single line. And finally, where we could put in the position, this is the same code again. It's just what's changed is how we're computing that at the beginning. And so if we do that example, now you can see we're running 40,000 objects at 30 frames a second, 40 frames a second. At this point, almost everything is happening on the GPU. So this is going to be very GPU dependent. If you run it on a desktop, it's probably going to run at 60 hertz. JavaScript is actually making about, I think, 14 draw calls, period. The only reason it's making 14 instead of 1 is that WebGL has a limit of 64,000 polygons per draw call. That's actually not per draw call, but if you use index primitives, if you know what that means, then you can only have indices that are 16 bits. So in this particular case, there's 14 draw calls. But that also means the CPU is actually probably sleeping. So you're not using a whole lot of battery, and the GPU is just doing everything for you. So to recap those things, in the simple case, order by model. If you're not ordering by model now, add that to your library. If you're using somebody else's library and you're running up to some performance issues, make sure they're ordering by model. If it makes sense, use the GPU for instancing. So a good example are trees. And this actually happened, I don't know if any remember the O3D beach demo. I've been too lazy to port that to WebGL. If somebody wants to volunteer, it's all open source. Originally, all the trees the bushes, the shrubs were all instanced. And that had 1,500 draw calls to do 1 frame. And to do the reflections and things like that required another rendering of the entire scene for 4,500 draw calls. Instead, we merged all those trees and merged all those bushes into 1 large model and got it down to 70 draw calls. And then, of course, it sped up significantly. Another one is tile-based maps. If you're doing any kind of platform game or any kind of old school game that uses a tile-based map, if you had a map on the screen and you were displaying, say, 40 tiles by 20 tiles, if you want to draw each tile individually, that's 800 draw calls. But instead, if you use some of these techniques, you could probably get it to be 1 draw call per row and still be just as flexible, and you would get it down from 800 draw calls to 20. That's a huge optimization. And then finally, visualizations. I don't know if any of you have seen the WebGL globe that Google just posted last week. You have a globe and you have all these little lines that you want to put all over the Earth or in your visualization. You could draw every one of those lines individually and it would go very slow, or you could somehow bake them into a mesh at runtime or offline and get it to run very fast. And then finally, if it makes sense, put the math in the GPU. So if you've ever seen the field demo on WebGL samples, all that grass is computed in the GPU, all its motion, all of that is just math in the GPU. JavaScript is doing nothing but passing in a clock. There's a particle library on the WebGL wiki. If you haven't seen it, I highly recommend that you take a look at the code. It's very flexible. You can put it in your own apps, and you can instantly add particles to your game with very little work. All those particles, all the math for them is running on the GPU, so they take very little time, and it's very flexible. You can do flames, you can do smoke, you can do fog, you can do ripples, you can do jet exhaust, whatever you need. Another one is simulations. I don't have a picture here, but there was a simulation of every meteor that's been discovered in the last 50 years. I think it has all 500,000 something meteors. And if you wanted to do that simulation live instead of in a video, you could do that very easily by putting all the data for those meteors into your buffers and writing a shader that used them. Past in time, what time you want to see the discoveries, and either show them or don't inside your shader. All right, so let's move on to post-processing. What is post-processing? Well, post-processing is almost anything you do to a photo in Photoshop. A few examples. One is blur. I'm not going to go over blur today because if you want to see blur, you can go look at the field demo that we wrote last summer. If you press D for debug, I think it'll bring up, show you how it's blurring, and you can look at that code. Color adjustments is obviously just doing anything with the colors, like this picture on the top right that's had the colors tweaked. And persistence is something you wouldn't do in Photoshop, but you might do in After Effects, and I'll go into that when I get there. So there's this really cool technique called color adjusting using a color cube. And basically, you have a cube that represents each axis, each color in a certain axis. So we have red across one axis, green across another, and blue across the third. And if you make one of these color cubes and adjust it to say something like this, and then you use that cube, you can map an image. So we'll take a pixel out of the first image. Let's say it's red. And of course, in WebGL, colors go from 0 to 1. So a pure red pixel would be 1, 0, 0. And we use that to index this cube. So we go over 1 in the red, 0 in the green, and 0 in the blue. And we pull that color out, and we use that to draw the image. To do one more, like we pull green out from a palm frond. This time it's 0.6 in red, 1.0 in green, and 0 in blue. So again, we go over 0.6 in red, 1 in green, which puts us at the back, and 0 in blue, which is still the top. We get that color, and we draw with that color. This is a great technique. I actually am not a video editor, so I don't know if it's in After Effects or Final Cut Pro or any of those, but I do know games use this a lot. One problem, though, WebGL doesn't support 3D textures. But fortunately, we can simulate 3D textures with 2D textures, so I'll show you how to do that. So the first thing is we take every slice of our 3D texture and we spread it out into a 2D texture. And then we're going to make a function that you can use in any shader you want, that you give it that 2D texture, you give it the coordinate inside the cube you want, in texture coordinates, and you give it a size. And when I say size, this size is how many units there are in the cube. So the cube I'm going to use in the example is 8 by 8 by 8. So this sample, in this case, size would be equal to 8. So the first thing we need to know is how big is one slice. And so one slice is obviously, textures always are referenced from 0 to 1. One slice is 1/8 in this case, since our size is 8. We need to know the size of a pixel. So a pixel is one size of the slice divided by the number of pixels. Again, that's 8. Now we need to know the size we're going to interpolate across. And we actually want to interpolate from the middle of the first pixel to the middle of the last pixel. And so the question is, why do we want to do that? Why not go from the very left to the far right? Well, here's the reason. If you have a 3-pixel texture and you use nearest filtering, you're going to get your image drawn up like that with no filtering whatsoever. But if you actually turn filtering on, what you'll notice is that it only filters from the middle of the first pixel to the middle of the last pixel. And so if we used the whole texture, we would get too much white and too much black when we're remapping. So we actually want to map from the middle of the first pixel to the middle of the last pixel, and that's why you have to subtract half a pixel. So now that we have that size, we can compute each slice. If we got passed in a blue of 0.6 and our size was 8, we'd figure out from the math above that we want slice 4. Slice 5, the next slice, is pretty straightforward, just add 1. Then we need to know how far into that slice to get a color. And so here we're going to add half a pixel, like we mentioned before, and then we're going to take our red, which is in texture coordinate X, and we're going to multiply it by that size that we computed before to get the right position. So in this case, if red was 0.08, you can see it comes to about the 7th pixel in that slice. Now we need to compute the position in each of the slices, since we want to pull out 2 pixels. And then finally, we actually pull out those 2 colors from those 2 slices. And here we've added in the Y component, which is green. And so if it was about 0.3, you can see we'd pull those pixels where the 2 arrows are pointing. Finally, we need to mix those 2 pixels. So this math computes how much to mix them. If we were passed in a blue of 0.6, it would come out with a value of 0.8. And what 0.8 means is that you can think of it either as a position, 80% of the way between slice 0 and slice 1, or you can think of it as 20% of slice 0 and 80% of slice 1. And in GLSL, you can do that with one line called mix. And so, demo time, what does that let us do? Well, here's a video you might have seen. And here I am adjusting the hue, say, plus 60 degrees, or setting it to all weird shades of blue with a little bit of yellow, or putting it to googly colors. I just went to some crazy things there. Or make it look like it's, you know, some 80s movie sci-fi thing. Or color negatives, or posterize it. Or make it super saturated. or make it sepia. And another thing you might notice is that I'm actually blending between two settings. I'm actually using two cubes at once. I call that function I just showed you twice to get the values from two cubes, and then I choose how much to mix them. So each time you pick a different setting, I interpolate between those two. And it doesn't have to be for video. Obviously, you can do this over any 3D scene, anything you can get into WebGL. So that's great, but how do you make that cube? Well, it turns out that's really easy. To make those cubes, you just take any photo and load it into Photoshop or some other video editing program or image editing program. And then you take a cube that's been stretched out and you paste it in the top corner. And after that, you pick any full screen adjustment. And as you adjust, you'll notice that it actually adjusted the colors of that cube. And that's exactly the cube you need. If you just take that texture out, you'll get what you needed to make that effect, to get the same adjustment that you made. Now, one thing here is that if you wanted to save time, and you guys are making apps for millions of users, you probably want to have the minimum amount of data. You would probably at this point take that image and crop it just to that cube so you can load that into WebGL. On the other hand, in WebGL, you have a whole library. You have the Canvas 2D library. And if you don't really care about this, the space, and these images aren't that big, I think they're like 60K or something like that, uncropped, then you could load that in, and this is what I do in the sample. I load that in, and then using the Canvas API, I just pull out the top 64:8. The reason I do that is that when I go to inspect my images, I actually have an image there, and I can see what the effect is. If it was just the cube, then it would be kind of hard to tell what that's really going to turn into. So I kind of like that, so I thought I'd pass that on. All right, let's go on to the next effect. This is persistence. And persistence is best explained with a demo, so we'll do the demo first. Persistence is adding a persistence. So you can see that these images with no persistence at this side are very sharp, and if I bring it over here, they start getting all blurry. And so I'll show you how to do that effect. So the first thing is we want to create 3 frame buffers. I'm going to call them new frame, frame buffer 1, and frame buffer 2. And the steps are, we draw to a new frame. We draw our normal scene that we didn't have persistence in to this new frame. We blend the new frame with frame buffer 1 into frame buffer 2. Then we draw frame buffer 2 into the canvas. And then we're going to swap those 2 frame buffers and repeat. And so I'll give you a diagram. Here's our new frame. We drew our scene. Our scene in this case is just a blue circle. It's in the top left corner. Here is frame buffer 1 in the first frame of our simulation or our app. It has nothing in it. So we blend those two, 50% each. We're going to get this in frame buffer 2. And then finally, we need to copy that result to the screen by copying to the canvas. And now we're going to swap frame buffer 1 and frame buffer 2. And by swap, I just mean in this second time, we're going to use frame buffer 2 where we're in the first step, and we're going to use frame buffer 1 in the second step. So here is them swapped. We have a new frame. We drew a circle in the middle. We have the old frame buffer 2 that has the circle from the last frame in it. We're blending those together into frame buffer 1, so now we have something with 2 circles. And you can see they're kind of fading. And we copy that to the canvas. We'll do a third frame. Here are the circles moved to the bottom right. We're blending with the last frame buffer we used as a destination before. And you can see now in frame buffer 2, we have the 3 circles, and we copied that to the canvas. And so if you play around with that, right, we have this example working here, but we're copying those canvases directly on top of each other. What if we skew how we blend them? We don't actually blend them directly on top of each other, but we move it a little bit. So let's say we move it a little bit to the left. We'll start getting a kind of a wind effect, or move it to the right, depending on how our persistence is. We can multiply it and make it kind of go out. We can rotate it and make it spin. And so what would you use this effect for? Well, you would use it for things like, a good example is Grand Theft Auto. So Grand Theft Auto uses persistence, and Grand Theft Auto on the PS2 uses persistence all the time to try to hide their atrocious frame rate. They also use it if you drink liquor in that game. Your character gets drunk and everything becomes blurry. If you were doing a platform game, you might say, well, when the person gets the speed power-up, make everything use this effect and blur across the screen. And you can also kind of see this is how, probably iTunes or some other things do their visualizers. They just keep drawing the stuff on top, and if you want to make some music visualizers, is another good technique. So the things about post-processing, they're very easy to add at the end of your project. You might be thinking you don't need them, and then at the last second you're like, oh, I can add some visual pizzazz by using this. Another great thing to do is that if you guys are making any Canvas 2D applications, there's a library out there called WebGL 2D.js, which you can Google for, and it implements the Canvas API on top of WebGL. And so what that means is you could check, does the user have WebGL? If so, use this. You don't have to change any code in your application, but now that it's in WebGL, you can apply these effects. So it could be that if the user has WebGL, he gets to play your fancy 2D game, but with added effects, like maybe the screen goes all radioactive when he's, when he's invincible, or you add like that kind of blur effect when he's going really fast, and if he's using the regular canvas, you skip that. And the other thing is that it doesn't have to be used in the entire canvas. In this case, I was calling it post-processing because I'm applying it to the entire canvas. But there are games like Metroid Prime where you have glasses, goggles that you look through, and only through those goggles is this effect applied. And you see infrared through the goggles, and outside the goggles you don't. Those kind of games, this is how they do some of those effects. All right, I'm going to go through a few WebGL do's and don'ts. Number one is never ever call GL get anything while rendering. And I've seen this in people's code. You can call, when you're looking up uniforms, you need to call get uniform location. And sometimes you want to check for errors, you call GL get error. There's a few other things you might query out of GL. You should be doing that all during setup. That's normal for experienced OpenGL programmers, that you should never call get anything while rendering. But if you're new, you might not have known this. The thing is that that's normal, right? It's just normal to set up your code so that you don't need to call it. One other thing you can do is for checking for errors is there are things we like to call internally debug contexts. And if you search for WebGL debug context, I'm sure something will come up. There's one on the WebGL wiki if you search for that. It's a function that wraps the whole WebGL context so that it calls GL error after every function. And that makes it very easy to turn on and off. You can, when you're debugging, you can turn that on, see if you get any errors, then turn it off and you're back to normal. You didn't have to affect the rest of your code with all your checks. And to give you an example, here is our 1,000 cube example before that was running at 30 to 40 hertz. It's now running at 8 because I'm calling GL get after every object. This is kind of similar, and it probably comes up less often, but don't attach render buffers while rendering. And what I mean by that, a good example is our persistence example. We had 2 frame buffer objects. And those frame buffer objects each have 2 render buffer objects. Render buffers are the actual memory that holds their data, and the frame buffer object is just state. A lot of people will make one frame buffer object and say 2 render buffer objects or 2 textures, and when they need to switch to what they're going to render to, they will attach the texture to this frame buffer object, do some rendering, attach a different one, and do some rendering. Well, that attaching is actually a relatively slow process. A lot of checks have to be made by GL. Instead, just make 2 or more frame buffer objects. The frame buffer objects just hold state. They hold a combination of render buffers and textures. And so you can make as many of them as you want. They don't take a lot of memory. They're just state. But that means you can do it all during setup. And when you do set those up, you also have to call check frame buffer status to see if they actually work. That is, again, another set call or a get call, like in the last example. It will really slow your code down. So do this all during setup, and it's all good. One thing to do is use requestAnimation frame. Up until this point, if you've done any animation in JavaScript, even in just regular HTML or with the canvas, the only way to do it was with using set interval or set timeout. The problem with those 2 functions are JavaScript and the browser have no way to know why you are using that function. Maybe you're writing a Gmail type of app and you are going to check for messages, or you're writing a chat app and you're checking for new chat things. And so even when your tab is hidden, or it's off the screen somehow, or your window is minimized, JavaScript or the browser has to call your function because it doesn't know why you're using it. So if you're rendering a game and it's off the screen, you're just going to sit there and kind of DOS the user's machine. You're sitting there rendering your game for no reason. He's not playing it. He's not looking at it. It's not on the screen. Whereas if you use requestAnimation frame, that's specifically for animation. It only calls you when your canvas is visible, whether it's scrolled off, whether it's minimized, whether it's under the tab, and so you won't DOS the user's machine. So I kind of like to put it, set interval, set timeouts for people who hate their users, and requestAnimation frame is for people who love their users. The fortunate thing is it's implemented in Chrome, it's implemented in Firefox, it's implemented in WebKit, or will be soon. And there are wrappers. They're very short. You could just search or Google for request animation frame, and I'm sure you'll find one that will just work across browser. They will fall back to the bad set interval or set timeout if they have no other option, but they will use request animation frame in any browser that implements it if it's available. So a few tips. One, consider stretching the canvas for performance. This might be obvious, but I think a lot of people don't notice. The canvas has two actual sizes. One is the size you actually render to, and one is the size it displays at, and those are separate. So in this top example, I'm setting the canvas size that I want to render to 512 by 512, but I'm saying display that at 100% of whatever my container is. And why would you want to do that? Well, if you're doing something complex, for example, the WebGL aquarium, it has fairly complex shaders in certain parts, and those shaders have to run for every pixel that get rendered. So if you have a 30-inch monitor and you have whatever that is, 4 million pixels, well, that's a lot of work for the GPU to do. Instead, you can draw it to a much smaller resolution. The actual aquarium only draws to 1024 by 1024, and then it lets the browser stretch that canvas. Of course, you're going to get a little bit of resolution. It's kind of like the difference between HD and SD, depending, but it depends on what you're trying to do. A lot of times, because you have a lot of motion in your apps, that stuff is hidden. It's a great way to get more speed. And video does this all the time, right? We take our small videos and we make them full screen. Even though the resolution of the video isn't the same size as the screen, it stretches. The very cool thing about working in WebGL is that almost all your apps are going to be 3D. And if you're doing it in 3D, almost every 3D library uses a function where you set your perspective matrix. You set your projection matrix to a perspective matrix. And there's always this function called perspective, and it almost in every library takes the same 4 arguments: field of view, aspect, and your Z settings. To make this work, all you have to do is set your aspect to those values. You get the canvas width divided by the canvas height. That's the size that the browser is using to display your canvas, not the size it's using to render it. And it just works. You didn't change anything, and you get speed. Another tip is send your users to getwebgl.org. And so there are ways to detect if the browser supports WebGL at all. And then there's also the chance that it can't initialize WebGL for some reason. Maybe the user's card is blacklisted, or maybe it's out of memory. For whatever reason, it might not be able to start it. In either case, if you send them to getwebgl.org, we can try to direct them to the best help for their situation. And I've seen some libraries kind of doing it themselves. They're like, oh, you can't run WebGL, download Chrome or download Firefox. Well, that's great until I'm running on a WebOS machine. That information is not going to be useful to me. And so the idea is that the Kronos group runs getwebgl.org, and you can go to the WebGL public mailing list, and you can tell them if there's any issues you want, if you want them to redesign this or you have some input. But basically, they will try to keep it up to date for all devices. And that's something that probably every developer out there is not going to do by themselves. The last one I'm going to put up is to use the WebGL Inspector. If you haven't seen the WebGL Inspector, it's very much like Pix for DirectX or GDebugger for GL. I won't tell you what it is, just Google for it, but I will show you it working. So here's an app you might have seen that came out last Thursday. I changed the texture so it would be easier to visualize. I was actually asked to review this app to make sure they weren't doing anything crazy, like drawing every one of those lines one draw call at a time. And I looked at the code and I wasn't exactly sure what it was doing. So I thought, I know, I'll try out the WebGL Inspector. So the WebGL Inspector is a extension for Chrome. There's also a plugin for Firefox. And it adds this little icon up here in Chrome. And so I click that, and it will reload the page with the inspector installed. And I'll tell it to capture a frame. And it's captured every draw call that WebGL made. And you can step through them down here. And you can see, here's the actual frame on the bottom right corner. But if I scroll down and I find the first draw call, which is here, and I click that, it will redraw the scene just using those first 17 commands as I click Command 17. And you can see in the bottom right, it's kind of hard to see because the lines are small, but that's the globe without the line. I can also look, well, what program was that using? Well, I'll scroll up until I find the used program before that draw call. I'll click it. Here's the program that was used to draw it. Here's all the inputs that it had, and as well as the actual source code for that shader. I can also look at the textures. Here's all the textures that are used. There's only 3. Here's the world texture. It shows in the bottom right. I could go back to the trace, and I could see that it's setting up a buffer here. I'll click on that buffer, and it'll show that buffer and potentially how it was used and all the data in that buffer. This is a great way to inspect your own program, find bugs, see what's going on, and look at other people's techniques and see what they're doing to include in your own. And that's pretty much it. All the samples that I've shown are available now live at webglsamples.googlecode.com. I put a bunch of links to libraries and other demos up here. You can Google for all of those. I didn't want to put links. Again, the hashtag, if you want to tweet about this, is #Chrome. And there's a link for questions, or you can come up to the mics if you have a question. Any questions?
Yep. Hi.
Hello.
How can we deal with different platforms, like a Chrome netbook that has an atom processor versus a desktop that has, a full-blown discrete GPU?
How can we deal with
different GPU
GPUs?
compared to the CPU in JavaScript?
Well, one thing you have to do is, do you mean like the timing, the fact that they're different speeds, or do you mean that they have different capabilities? Okay, so the question was how to deal with different GPUs. And the easiest way to do that is either to do something like they do on the PC and ask people what features they want, or to structure your code. You could do a timing and you could see, is it running too slow, and say, take some features out. The other thing you have to do is just, that's what, it's a hard question, because you could be running on a desktop that has, say, the highest end GPU, the newest one with 2 gig of RAM, or you could be running on a low end GPU like a G1, the original Google phones. I don't think it can even run WebGL. And I don't really have a good answer for that, other than to either add some options and say have an SD version and an HD version. I know some games that do that. Or just structure your code so that you can fall back if you run out of memory. Like texture the things that are important first, and the other things that are less important later. Yes, sir.
This might be slightly off topic. So I've been watching the Firefox team implement WebGL.
Okay.
And they've been having a pretty large share of problems dealing with platform-specific driver bugs. And while dealing with that, they've been very active in the driver community, asking lots of questions, contributing, filing upstream bugs. The Chrome team has been completely silent, at least from the Linux driver perspective. And I was wondering if that's simply because you guys had relatively little challenge with implementing WebGL, or is it just a team policy?
So I think the question was, there's been a lot of talk from Firefox about talking to the various graphic driver manufacturers about issues with driver stability, in particular Linux, or just in general.
Well,
and you haven't heard much from Google. Well, I can tell you that the chairman of the WebGL group is now Ken Russell, who's on the Chrome GPU team. And he's probably the most vocal guy ever. That he isn't being vocal in public, I think that's just happenstance, because he's very vocal internally, and he's very vocal. I don't think it's crossed his mind that he needs to be more vocal in public, and I'll bring that up with him. He is heading the charge to get the ARB robustness stuff into the drivers, and to make sure that all these issues are dealt with, both for platforms in general and including Linux.
okay, thank you.
Just a sort of platform-specific question. Honeycomb tablets with Tegra processors, NVIDIA chips. When do you see WebGL making it to mobile WebKit?
When do I see, so the question is related to tablets and them having good GPUs, when do we see WebGL making it to mobile WebKit? I don't have an answer for you on the WebKit front. I do know that it's available in Firefox right now. You can download Firefox for those machines, and it will run WebGL. I've been told that it's not, it's still very beta, and there's not performance optimized there yet, but it does work. I've seen demos come up.
Great, thanks.
I actually, yeah. I actually have seen it running in WebKit in certain places, but when it'll be available, I have no idea.
There's been a bit of press about security vulnerabilities exposed by WebGL. Are you guys doing anything to address that?
So the question is, there's been some security vulnerabilities that just came out, I think it was yesterday, in WebGL, and what are we doing to address that? Well, we're taking that seriously. Obviously, Chrome's like main thing is that we're all about security. And Chrome in particular, we actually run all our GPU processing in a separate process. So like we do for other things, even if somehow a web page was able to execute code in the process that actually runs your web page, it's not allowed to call GL at all. Or at least if it does call it, it can't call it with any parameters that we don't approve. That said, we're taking that very seriously. We're with the Kronos group and discussing with the other browser vendors to decide what to do. We're working with the driver manufacturers to make sure that all these issues are covered, because they know that up until this point, it's always been you installed an app and you trusted that app when you installed it, and it's changing to this new web model where things are supposed to be not trusted and you just have to make yourself secure. And so we file every bug we can. We blacklist any card that we find that has a problem. And that's why so many cards are blacklisted right now. Any card before 2009, January 2009 is blacklisted, and other ones that we find bugs in.
Okay, thank you.
Any other questions? So the question was, what's the performance penalty for the sandbox in Chrome? We're actually not sure. My personal opinion is that we actually run faster. And the reason is that we are basically multiprocessing your app. Because what we do is we take all your WebGL calls and we serialize them through a command buffer, and they actually get called by another process. And that means that your WebGL code is able to issue them much faster than it could without that, and then some other process is able to spend the time doing the hard work. And there are issues. We have flow control issues that we keep working on, that we get more speed, and then we add something else and we break that and we get a little less speed. But ultimately, we should be able to run faster because of our sandbox, not slower. Any other questions? All right, thank you very much.